Welcome to video number 3 in our sequences and series sequence of videos. The last one was a little bit long. I needed to introduce a lot of new terminology, and I will make this one much shorter. A geometric sequence also has a very identifiable pattern. In this case, multiplication. If you look at this sequence, you will notice that we multiply by 3 between each term to get the next term in the sequence. We call this, instead of D, the common difference, we call this the common ratio, and the common ratio is symbolized R. So R is equal to 3. Now what if you weren't really sure whether 54 times 3 is 162? If you just simply take the next term, take a term divided by its previous term, you will always get R. So R is 6 over 2, which is equal to 18 over 6, which is equal to 54 over 18, which is equal to 162 over 54. All must be equal to be a geometric sequence. So if you are looking at some messier numbers, just pull out the calculator, do that little gizmo there, and you can figure out if it's a geometric sequence. Once again, if we were to number these sequences, and I meant to leave a little space for this, but if we were to number these, so n would be 1, 2, 3, 4, 5, and this is our a sub n. If we were to plot these points, and I'll just do it right down here. 1, 2, 3, 4, 5. Notice we're going up pretty high here, so why don't I say 10, 20, 30, 40, 50, and 60, and we're not going to go all the way up to the 162. But if I were to plot the points, I'd have 1, 2, which would be very close to the x-axis. And then I'd have 2, 6, which would be about right here. Then I'd have 3, 18, which would be close to the 20. Then I'd have 4, 54, which would be clear up here. And you might recognize this as an exponential pattern, because in an exponential pattern, we have this constant multiplication. As n goes up, our domain variable, like our x, goes up by 1, we multiply to get the next value in the y direction. So this is an exponential pattern. Once again, do not connect the dots. So geometric goes with exponential, arithmetic is linear. Now to write a recursive rule, we think in our heads, start with 2 and multiply by 3 each time. So we say a sub 1 is 2, and a sub n is the previous term, a sub n minus 1 times 3. So remember, we have to say for n greater than 2 or equal to 2, then we use our rule. So there's our recursive rule. Remember, you have to write the whole thing for that to be the recursive rule. So in general, we would say a sub 1 equals whatever blank, and then for n greater than or equal to 2, a sub n equals a sub n minus 1 times r, or we could say r times a sub n minus 1, either way. So that's our recursive rule. We could use that to continue to generate terms by multiplying the previous term by 3. To get the explicit rule, we look at a similar pattern as we saw in the arithmetic. We recognize that a sub 1 is 2, a sub 2 is 2 times 3, a sub 3 is 2 times 3 times another 3, a sub 4 is 2 times 3, which is 6, times 3, which is 18, times 3, which is 54, etc. So a sub n is 2, and when I'm multiplying repeatedly, that's an exponent. So I can say this is 2 times 3 to the first, a sub 3 is 2 times 3 squared, a sub 4 is 2 times 3 to the third. I could say a sub 1 is 2 times 3 to the 0. So in general, a sub n is 2 times 3 to the n minus 1. So we have an exponential function, which is what we expected. So there's our explicit rule. In general, we would say for the explicit rule that a sub n is equal to a sub 1 times r to the n minus 1. And hopefully some of these little rules will look familiar to you from Algebra 2. So this is a try this problem. Write the recursive rule for this function, and then write the explicit rule. And obviously you have to find r. Write the explicit rule. Find the 20th term. So if you want to pause the video, you can try this problem, and then I will talk through it when you resume the video. So for number 1, find r. This is where I'm going to say r is negative 150 over 200, which should also be the same as 112.5 divided by negative 150, which is the same as negative 87.375 over 112.5. And if you do that on the calculator, you will find that r is equal to negative 0.75. So our recursive rule would be a sub 1 is equal to 200, and for n greater than or equal to 2, a sub n is first term 200 times negative 0.75, negative 0.75 to the n minus 1. Actually, that I just wrote the wrong rule. Excuse me. It's a sub n minus 1 times negative 0.75. And it might actually look better to write it as a sub n equals negative 0.75 a sub n minus 1 and put that in front. So that's recursive. Explicit rule is what I just wrote before. A sub n is equal to a sub 1, which is 200 times negative 0.75 to the n minus 1. That's the exponential function. It's not strictly required to write n as an integer, a positive integer here. However, you should recognize that this is true where n is a positive integer. When you write the terms a sub n, it's usually recognized that that represents a sequence where n is a positive integer. I meant to tell you earlier why we use n instead of x, and this is why. N in math represents the natural numbers. So we use, or often the integers. So we use n when we're talking about positive and negative whole numbers. So in this particular case, positive numbers when we're talking about a sequence. Okay, number 4, find the 20th term. I didn't actually number these, so 1, 2, 3, and 4. Find the 20th term. So for finding the 20th term, I would say a sub 20 is equal to 200 times, and I wrote the decimal place in the wrong place there. I apologize. You're probably screaming half point by now. Negative 0.75 to the 19th. Now this is a messy number. Use your calculator. Use calculator. And I confess that I don't have a calculator handy, so I'm going to pause for just a second, calculate that, and write the answer down so that you can check yours. The correct answer for that is negative 0.8456 517, etc. So you should get that number. Remember that exponential functions have the most rapid change of any type of functions we've studied so far, so they are going to get very quickly big or very quickly small. Notice that when we have an exponent or a base of our exponent that is less than 1, this is less than 1, we are going to have a decreasing exponential function. And so the bigger, the more terms we add, the closer the terms will get to 0. Terms a sub n, the terms will approach 0. If this number, the base, for example, in our first example up here, where our base was 3, the terms are going to get infinitely big. Terms will get infinitely big. And this distinction is going to make a big difference when we talk about geometric series, particularly infinite series, in a subsequent video. And that's the end for this one.